Okay, everybody, we have one last topic to get through this semester, and it is the topic of numerical algorithms, methods for solving linear systems, working with matrices. And there's a lot more to this subject that we're going to get time for this year. But we're going to talk about a couple of algorithms, one of them being really familiar, one of them should be very, very familiar from a linear algebra standpoint, and that is simple Gaussian elimination. Of course, I guess like when I learned that topic myself, you understand the idea of row operations and like single steps, but it often, I don't know, felt to me, you do random things until you get this triangle of zeros in the bottom left corner or whatever. But there's an actual like, you know, um, algorithmic process to get the job done in general. And so we're gonna go over that, remind you of how it works, and then try to translate that into some code. And I'm gonna give you some source code at the end of the day to work with. But in our last lecture, or the one to come, that is where we're going to go a little bit further and talk about some improvements to that scheme using kind of an interesting, different idea. So for now, it's going to be a bit of a review of some matrix stuff that should be pretty familiar, and an example, and then a little bit of coding. So why don't we get started with it? Algorithms for solving systems of equations. It's actually a much deeper topic. We're just going to scratch the surface here. Really, we could go a lot further, and I was encouraged to see that many of you are working with some more advanced methods as part of your final project, which is really cool to see. But we're going to get done some basics here. So, all right, for all of this, we're going to start with a review of square matrices and linear systems. We're going to consider this matrix. So it's just a square matrix, that A11, A12, all the way through to A1n and so on. This is a matrix, defined as such, like nothing special about it. The m and the n are integers here, defining the number of rows and columns of the matrix. And of course, this A is square if m and n are the same size. So I was going to say A is a square matrix if square, no, I meant if m is equal to n. So no surprises there. It's going to make sure it has the same number of columns as rows. But as a review, square matrices are generally really useful and have many properties that we should know. We can calculate the trace and determinant of A. Of course, the trace is when you add up the elements of the diagonal. The determinant is given by, well, a series of operations that can be calculated for any square matrix. Okay, we multiply any two square matrices together, we should obtain a square matrix. And in addition, we might calculate the inverse of A as long as A is, well, invertible. And of course, that comes down to a bunch of different properties. You could say that the determinant has to be non-zero. There are a few different ways that you can work with that. And you can calculate matrix powers like a squared, a cubed, just by multiplying the same matrix together many times. With a square matrix A, you can determine eigenvalues, and eigenvectors associated with A. And if A is a full rank matrix, you can use A to represent the left side of a system with n equations and be able to solve uniquely for n unknowns. Full rank simply means that none of the columns, none of the rows are not linear combinations of any of the others, right? So that means that an n-dimensional space is spanned by the column vectors, is I think the official definition of that. In any case, a matrix like that is one that could conceivably lead to a system of equations having a unique solution. And it's that last point that we're going to be focusing on for this last section, is actually solving these equations. Okay, so given an n by n square matrix, of rank n and an n-dimensional column vector b. So that's what we have here. We want to solve the linear system of equations given by matrix times vector equals vector. And this is a vector of constants. This is our matrix. And this is the solution that we want to figure out what x satisfies that. And it's just a really elegant way of writing down a system of equations like ones that you were introduced to in grade 10 and 11. And you can, from linear algebra, solve for the variables by employing Gaussian elimination upon an augmented matrix, where you take the matrix A and you represent that vector of values on the right side of the equation, the items in B, and you row reduce this down, which is really just the same thing as using elimination as back when you first learned systems of equations, right? I think that a lot of students get paralyzed by linear algebra when they think of it as this abstract box of numbers where things are different. But all you're really doing when you use Gaussian elimination is taking a certain number of times a particular equation and subtracting or adding a particular number times the other, which is a strategy that you used years ago when you first started solving systems of equations. It's just represented in a more convenient way. So don't be scared of it. It's we can do all the things that you're familiar with from, like, think of grade 10 and 11 concepts. Right? If you know that one equation holds, then a multiple of that equation also holds. If you know that there's a relationship that x plus 2y plus 3z is equal to 5, then it must also be the case that 2x plus 4y plus 6z equals 10. If I multiply that equation by 2, it still holds, right? That's why you can take a multiple of any row in order to solve a system. And in the same sort of for the same sort of reasoning, you can take a combination of two rows. So you can replace one row of a matrix by a multiple of that row added to a multiple of any other row. As long as you're replacing rows of matrices that represent equations by information that includes that equation, you're good to go. You're maintaining what you have, but hopefully you're getting to a situation where it's represented more conveniently, and you're reducing the system to something that's more readable at the end of the day and easier to solve. And then finally, you can swap the placement of two rows when you're solving systems like this. The goal using these steps is to arrive at a UT, an upper triangular matrix of this form. So you have this triangle of zeros right here. Triangle of zeros. And of course, the benefit of that is that, well, if you think about what this means, there's a multiplication involved here. We're left with, these are the only non-zero elements in the bottom row. And you'd be able to say that AMN times XN, the nth component of the solution vector, which is kind of implicitly shown in this representation here, equals whatever the Bn is, whatever this column is that's right here. So this isn't the original, this is not the original B column, and this is not the original A entries, right? This is all after reducing it down to something of this form. So this is actually a little bit of like different entries at the end of the day. So so these are the values after the reduction is complete. Right? The only reason I say that is because, I mean, when I first introduced it, I was like, oh, we have a matrix of this form with all these different A values and all these different B values. But after applying all those row operations, well, those B values are going to change over time, and those A values are going to change over time. But then I don't want to introduce new awkward notation, say, oh, it's now like alpha 2 and a beta, like something like that, right? I just am trying to show that we want to get it to this form where we have possibly non-zero entries in these particular spots, but we must have zero entries in these other spots. That's all that I'm trying to represent here. So the point is that the first non-zero entries on each row have to occur with the entry on the main diagonal. So the diagonal entries reading from left to right are the first ones that are potentially non-zero, right? A11, A22, everything to the left of those have to be 0. That's what our goal is. That's where we want to get to. That puts the matrix into row echelon form. And that provides an advantage in that we can solve for those variables by easily using back substitution. Find the last x value, use that and sub into the line above it. Use those and sub into the line above it. And go all the way back until we've solved for all of those different variables. Okay, all of this, I mean, I know it's been a year for many of you, most of you, right? But it should all be reviewed from linear algebra. But I think it's really good to understand it fully before we try to design a computer algorithm. Because what we're going to do, right? Matlab is excellent when it comes to linear algebra, when it comes to vectors, when it comes to matrices. There are a few tricks that are involved that can help to put those together, to work with those rather in different applications. And I have some code at the end that we'll go through quickly so that you can see that you can actually take a matrix and use these operations and actually program a computer to do them without too much effort at all. Like you can do this in a small number of lines. Okay, so let's understand how this works though. We want to do it in sort of a sequential format wherever possible. Instead of like thinking of doing random operations here and there, let's use Gaussian elimination to solve this system. Again, hopefully this is review, but it's this. We're going to solve the system of equations given by x1 minus x2 minus 2x3 equals minus 7, 3x1 plus x2 plus x3 equals 14, x1 minus 4x2 plus x3 equals minus 25. So this can be represented as, and I will write this, I don't know, pretty carefully to start with, just to remind you how this works. So this is, oops, not x. 1 minus 1, I'm taking the coefficients from all of these numbers, or from all of these terms rather. 3, 1, 1, 1 minus 4, 1. Those are the coefficients for all of these terms right here. I am multiplying this by x1, x2, x3, and then by the laws of how matrix multiplication works, that produces this system. And on the right, we have that vector of values, the b vector, if you will, which was minus 7, 14, and minus 25. Or, as an augmented matrix, this. We're going to go with 1, minus 1, minus 2, 3, 1. Take your time with this. It's so easy to just accidentally put in the wrong sign, and then you get screwed. The problem, of course, with any linear algebra stuff, one little mistake tends to cascade, and then everything looks like a nightmare. So just be particular, be careful, and you'll be okay. All right, so we all have our ways to do it, but again, we want to be sequential, and the way to do that, right, is to establish what's called, you might call it a pivot. So I'm going to use as a first broad step, I'm going to use this top left corner. I need that top left corner to be there, but I want to eliminate both of these values first before I ever think about this one right there. I'm looking for the triangle of zeros to occur right here. So there are going to be 3 different operations I need, at most, 1 for each one of those numbers. But I'm going to work on these 2 first before I establish a new pivot that would be in the next diagonal. So that's how we're going to go. And people have different notations. I'll show you what I'm going to use here for you. I'm going to, so copy that top row. We're not going to touch it. That's fine. I need all of those entries there. But I'm going to replace row 2 by 3 row 1 minus row 2. And by doing that, right, I'm using a linear combination of 2 rows that includes row 2, so I'm not losing any information about it, but I'm going to gain a new equation that has to be true as well. So I'm going to be using that, and let's see. the combination 3 row 1 minus row 2 is guaranteed to stick as 0 right here, because 3 times 1 minus 3 is 0. At the same time, 3 times minus 1 is minus 3, minus another 1 is minus 4. So I'll put that right there. And 3 times minus 2 is minus 6, minus another 1 is going to be minus 7. 3 times negative 7 is negative 21, minus another 14, looks like minus 35. And using the same number, right? Don't start changing things up or whatever. We want to be sequential. We want to be precise. And we're going to formulate an algorithm out of this. We now want to work on eliminating this one. So that's going to be row 1 and row 3 that are involved. And we're going to replace row 3. I think it's pretty clear. We want to take row 1 and subtract row 3 because 1 minus 1 is 0. So some pretty simple operations here, but be, again, careful. Minus 1 minus minus 4 is 3. Minus 2 minus 1 is minus 3. And minus 7 minus minus 25 is plus 18. Yeah. I did this in advance, but I'm trying not to look at my notes because it keeps me, I don't know, honest. Okay, so now that we've got this, we are happy. This is good. We don't want to touch that. So we're done with row 1, right? Because if we were to use row 1 to try and eliminate the bottom row, this 1 is going to screw us up. This 1 up here in the corner is going to contaminate our 0 that we got there before. So the idea is now use the next diagonal entry down as your new pivot. Use this as the thing to pivot with, and we're going to use that to eliminate the 3. That way, you can kind of see how this is going to turn into an algorithm, turn into some code. We're going to take each diagonal entry at a time until we get to the second last one, and make sure that we are subtracting using that value on the diagonal in combination with the different values that we're trying to eliminate to make zeros in each spot that we need. That sounds like a nested loop, right? We're going to go from 1 to n minus 1, thinking of the dimension of the matrix, and then within each one of those, we're going to go through and calculate what we need to get the zeros there, but manipulate the whole row that way. So there is going to be some sort of nested loop action happening. But some Matlab code, some nice commands will make that easier for us. So anyway, we haven't finished this problem yet, and I'm getting a little bit ahead of myself. I want to put a 0 here. And I need to use that pivot, that minus 4, to get there. So let's see. We're going to replace row 3. Let's copy out those top 2 rows because those aren't changing. It's only that bottom one that's going to change now. So 0, minus 4, minus 7, minus 35. And we're going to replace row 3 by 3 times row 2 plus 4 times row 3. Perfect. I get a 0 there because, of course, 0 and 0, it doesn't matter what combination I get them in, it's 0. And then that combination is going to give me a 0 right here. We have to think about what's going to happen in the third column. But 3 times minus 7 is minus 21, plus minus 3 times 4 is minus 12, minus 21 and minus 12, minus 33. This combination, this starts to get a little bit grisly looking, but it's not so bad. 3 times 35 is minus, or well, the minus 35 is minus 105. We're going to add 4 times 18. 4 times 18 is 72. So minus 105 is 72. I think it makes 33 on the negative side. And look at that. The numbers work out so nicely. The thing is, we have that triangle of zeros. This is our row echelon form. If you wanted to, you could do some additional operations to turn these into ones, but it doesn't really matter. Let's work on back substituting. From row 3, negative 33x3 equals minus 33. Of course, that means that x3 is equal to 1, and we're 1/3 finished. From row 2, we have minus 4x2 minus 7x3 equals minus 35. And of course, with x3 being 1, we get minus 4x2 minus 7 times 1 equals minus 35. That means that we're going to be adding 7 to get minus 28 and dividing by the negative 4, I think x2 has to be 7. All right, and then finally, row 1. We have x1 minus x2 minus 2x2, 3. Let's try that again. Minus 2x3 is equal to negative 7. We know that x2 is 7. We know that x3 is 1, and we can use that to finish the job. So minus 7 right here, and minus 2 times, 1, equals minus 7. Take the negative 7, add 2, we're at minus 5. Add 7, we're at plus 2. And we get x3 equals 2. So there we go. There's our solution. And we did these in sequential steps, right? We established the correct pivots. We had 2 operations for the first one, and then 1 for the next one. You can see that in general, if you have like an n-dimensional matrix, you're going to have like n minus 1 steps to begin with, and that number is going to fall by 1 until you get to the last column that needs to be dealt with, where we have 1 step remaining. So we have like a decreasing number of steps with each one. Once we're at a solution, or once we're at that row echelon form, we have to do the back substitution steps, which then is also going to take some coding that needs to read the different numbers of the matrix and do the necessary divisions and subtractions and so on. So there's stuff to think about there, but that's kind of how it works. Okay, so let's think about this from like an algorithmic perspective. What happens if we want to code this? Okay, I know full well that there are automatic solvers out there. That's not the point. The whole point is to think in terms of the logic behind them. Why do they work? How do they work? If you wanted to code one yourself because, the world exploded or all computers die because of, I don't know, like if you had to figure out how to create this sort of thing yourself, how would you do it? I think that's a good little puzzle to figure out, because we have the algorithm. We know how to do those steps that we just did. How do we tell a computer to do the same thing? Okay, as we saw, we need some sort of main loop, and that's going to be to go through all of those different columns where we're trying to put the zeros in place. So the number of columns that we need to put the zeros in place is n minus 1, because, well, the last one, we don't need a 0 in place. We need a triangle with like a number of entries that's 1 less than the total, width of the matrix. So n minus 1 main iterations, but within each one, we need to use that pivot, which is the ith diagonal entry on the ith iteration. And we want to eliminate all entries below it. So we're going to need to use the value of that diagonal entry, whatever it is, and use just the right subtractions to put a 0 in place. But how many do we need? Well, I need to go through all the different rows that are below it. I need to do another loop, one for each one of those. So that's going to be interesting, because the size of that loop will also depend on how far along we are, because there are less and less and less and less calculations to be made. So we're going to have to think a little bit, right? The length of that loop depends on how far we are into the algorithm, which is, it's not super complicated, but it's an important consideration. With each iteration, we update the matrix with a new matrix, which will have extra zeros in all entries below the current diagonal entry. Once you've done this, once you've gone through all of the columns and you've done this, your matrix, hopefully, if you've done it right, will be upper triangular, i.e. we have that triangle of zeros down there. And you can then obtain the solution through back substitution. Now, I think that we understand the idea of row operations to put the zeros in place, and that I have to use some number that is for those eliminations that require the value of the diagonal and the value of whatever the entry is that you're trying to eliminate. That's probably not hard. What's interesting, though, is trying to find a formula for back substitution. It's easy to do it by hand, right? It's easy to just take things and say, oh, you just have to divide this. And for the next one, you just take that value and, you can just solve for x or whatever to figure out the next one and so on. How do you automate that? Okay, well, let's do it. Let's do it. I had to figure this out myself. To be honest with you, before teaching this course, I'd never actually coded this myself. And so trying to figure that out was interesting. And I ran into this problem where I'm like, oh, how do I do that? I need some sort of general general formula to try and do that back substitution. So suppose we have this upper triangular matrix right here. This bottom row is ready to go, right? If you've got it in that row echelon form, you've got a square matrix on the left, you should be able to do that first calculation for free, right? To find the xn, you have amn, you could say ann because the m is equal to the n, but whatever, is equal to the bn, times the xn rather, is equal to bn. That's what this says. And so if you wanted to solve for this thing, well, you're gonna get xn equals bn over amn. So that's not a problem. So I'm just checking to see if I have my notes, because I did do this in general, but I wanted to just make sure that I wrote down the right things. But I think I think you're good to go. Okay, so imagine now that we have, well, the one above it. So if we had xn minus, or sorry, we've solved for xn and we want to solve now for xn minus 1. Let's look at the second to bottom row. Okay, the second to bottom row, well, see, it's A11, A12, A through A1n. The next row is A22 through A2n. The second to bottom row is going to involve am minus 1, n minus 1 in the like, that's on the diagonal. And then the one right above it is going to be am minus 1 an. Right? So let's try to put that into place. We're going to have a m minus 1 n minus 1. That's going to be times x n minus 1. Thinking of the multiplication and stuff. Plus a m minus 1 n. That's times xn. We know what xn is. That is to equal b n minus 1. Okay. So that's what we have, and our job is to solve for this one. We already know what xn is, right? If we've already solved for xn, we will have this in our code already. We'll have that value. So we're trying to figure out what we need to do here. Let's solve for xn minus 1 and see what that looks like. Xn minus 1 is going to equal, well, we have this bn minus 1. So let's use that. Bn minus 1. We're going to need to subtract this term right here. So minus a m minus 1 n xn. And this is going to be divided by that am minus 1 n minus 1. Okay, so it's divided by that diagonal, right? am minus 1, an minus 1 is that next diagonal entry up. So that's the division there. And look, in the first step, we divided by this diagonal entry, the one in the bottom right corner. So it looks like we're always going to be dividing by the diagonal entry, the next one up. But each step, okay, we had a bn on the top before. In this one, we're going to be taking bn minus 1 and subtracting this quantity right here. Let's see if we can establish a pattern by doing this one more time. So if we do a xn minus 2, and we kind of extend this whole thing, we're going to get here a m minus 2, so the next diagonal up, this is xn minus 2, plus a m minus 2, but n minus 1, again, moving over one column, that's xn minus 1. And then we're on the right, so we get a m minus second row and n x n. This is going to equal the n minus second entry in that b vector on the right. Okay, at this stage, we've solved for xn, we've solved for xn minus 1, and now we need to solve for xn minus 2. So we know this one, that's given by this ugly thing up here. And we know this one, this was our very first step, that's just this little quantity right here. And you see how we can kind of sequentially do this? If we have one value, well, this entry might be really awkward, but it's just going to be a number at the end of the day, and we can draw from that and put it right here in this entry right here, and so on. If we solve for xn minus 2, we get xn minus 2 equals, same sort of idea. Bn minus 2 is going to be on the right. I subtract off the things that I have. So minus a m minus 2 n minus 1 x n minus 1. And then I'm going to subtract off this last term here, which we already calculated as well. A m minus 2 n x n. And we are going to divide all of that by, again, this quantity right here, the next diagonal entry up. So it's a m minus 2 n minus 2. So you see this pattern, right? At every step, it looks like we're taking, well, the next b value up. We're subtracting some things, and those things are pretty predictable, right? Those things, look at, we have a m minus 1 n x n. In the next step, we have an a m minus 2 n minus 1 going with n minus 1, and a m minus 2 n x n. The m minus 2 goes with the n minus 2 that happens right there. So this minus 2 is going to match that minus 2. This n minus 1 and n minus 1 and n, those match as well. We're subtracting off kind of a series that is building with every single one of them. And they're very predictable. There's a pattern to it. And where there's a pattern, we can translate it into an algorithm using just the right coefficients, just the right vector entries, just the right index to make sure that we're matching the right quantities to the right quantities. So we're going to take the next b value, we're going to subtract off the right products that are determined with just the right indexes to make it work out. And once we've got that sum, we're going to divide by a diagonal entry, right? The next one up that's corresponding, right? Because look at xn minus 2 always goes with this diagonal entry with the minus 2s. The second, the m minus 2 and n minus 2 would be the third to last one. And we keep going until we get to the first one. We do this all the way until we get to the very first one. You see why it's tough to program? Because of the fact that it's not like a set number of terms, we actually need to create a loop for the back substitution that will continue to subtract off those terms in the top until we get through everything we need to subtract, depending on how many variables we've calculated for already. So it's not trivial, but it can still be done very concisely. It's tricky enough that I wanted to produce some source code for you so that you're not wrestling with it yourself, so you can instead spend your time looking at my code, reproducing it, and thinking through why things have to be what they are, okay? So, hopefully that was okay. I know it's really tricky to think about, and it's weird to try and come up with general formulas, right? Like, it's not hard to row reduce a matrix, but it's hard to kind of think algorithmically how you do this. Okay, let me tell you about a couple of Matlab things. We'll finish off this lecture. Using matrices in Matlab, I mean, I talked about matrix commands earlier, so I didn't want to get into a huge amount of detail here. However, I wanted to point out one extraordinarily useful command in Matlab, and it is, if you have a matrix, I called mine aug_m because it's like an augmented matrix, then basically you can use, instead, so if I wrote, like aug_m1 2, that's going to refer to a particular entry of the matrix, right? Row 1 and column 2, and give me that entry. But if I want to take an entire row all at once, I can put a colon in place of the particular column. And what that does is it gives me an entire vector of values at once. That way, I can replace an entire row at a time instead of having to do it entry by entry by entry. That's really important because if I'm taking like 2 row 1 and I'm subtracting row 3, it's nice if I can just take 2 times 1 vector and subtract another vector and replace the vector all at once. instead of having to do a loop and go through and calculate every single entry. So this command is extraordinarily useful, and I highly recommend that you understand how it works. So that is going to be really important. There's a couple of other things that I have here. I have, let's see. So I have an initialization of the system. So we have an A and a B, and the N just tells me the size of the system so that I know how big my loops have to be. So this is fine. Okay, this is a cool command. This is just me making an augmented matrix out of the different variables that are there. Okay, notice that I have a B with a little tick mark. That's to give me the transpose to make sure that I'm using the right kind of vector to augment the matrix, so that it doesn't get like appended on the bottom. It gets appended on the side instead. So note that I take the transpose of B here. To correctly augment the matrix. Okay. Otherwise, here's the issue, right? If I didn't do it this way, it would be trying to take this matrix right here, which is defined by 1, -2, -1, 2, and so on and so forth, and a B vector, which is defined here as what looks like a row vector, and this right here and this right there don't augment correctly, right? I can't just append this. I would get a matrix that's shaped like a frying pan, right? Like I would get something that would require 3 by 3 right here appended to, this. I need to flip this first. I need to take the transpose for that to be defined properly. And so that's what that step is doing. Okay, so that's cool. One funny thing is that I think that I meant for the system to be the same as the one that we did in the example, but I actually changed the B values here. So it's not going to give you exactly the same results. They'll be uglier. Because I think I changed the example so that the numbers were easier for us to do by hand. But then I didn't update it here. Oh well, it's fine. Okay, so the row reductions. Note, we have this outer loop. The outer loop is n-1 big, so we have to go through n-1 major iterations, and then within each iteration, we get smaller and smaller and smaller loops that determine the actual operation. So I want you to see the index in here, I plus 1 to n. If I just zoom in a little bit here, it might be easier to see. But notice, if I is going from 1 to n-1, imagine if n is 3 here, I'm going to do 2 major loops. And in the first loop, my j is then going from I plus 1 up until that 3. So I'm going to go from 2 to 3 because I only want to do those row operations on the second and third rows, right? So that's kind of what this is for. And then in the next loop through, it's going to go from 3 to 3. So you see, then it's gonna do the things that I need to do. This here looks really, really ugly, but I want you to check out what this does. I'm replacing aug-m, j, and colon. As we talked about, that colon is going to take the whole row. So this here, I'm replacing a whole row of the matrix and redefines that whole row of the matrix aug-m according to something that's determined by the row operation. Look at what this is. All it's taking here is that entry times the whole row, which is great, and then subtracting the diagonal entry, the one above it, times that whole row, right? So it's doing a row operation. It's taking the one times the right entry, subtract the second row. That's what it's doing. And if you remember that these colons represent entire rows, and these single values here, aug-m, ji, they represent just numbers, right? They're an entry. It's comparing these two entries, multiplying by each other and subtracting them to ensure that I get a 0 in the right spot. But I have to update the whole row by that operation, which is why I am replacing a whole row by that. So hopefully that makes sense, and you can parse that one piece at a time there. It's not straightforward, especially when you're a couple of indexes deep. But It's just reflecting what you would always do with those row operation steps. Okay, and then you do that loop. This nested loop is literally going to do this everywhere that we need that to happen. Okay, let's zoom out a little bit here. And once we've got it into row echelon form, so at this point, we have row echelon form, and what we have to do then is actually do the back substitution. I find that the indexes are really tricky here, but I just want you to recognize what's happening. The very first one, xn, notice that I'm just using that very first formula. This is the very last variable in that vector, that xn, so we only have a single division to do. So this one, I'm just going to do that first one. So I'm going to say calculates xn as a start before I jump into that loop. Because once I get into the loop, my entries are going to depend on the previous xn's that I found. So I wanted one to start with, so I could start referring to it. And see, look what I've done here, a really funky loop that starts with n minus 1 and then goes backwards by minus 1s. If I zoom in just a little bit, starts at n minus 1 and goes backwards by minus 1 until I get to 1. Because I want to find now xn minus 1, then xn minus 2, then xn minus 3, until I get back to x1. And each one's going to depend on all the ones before it. Okay. So that's what's happening here. So I'm going to zoom out a little bit more here, and then you'll notice that all of these we're taking basically a sum of the different quantities that we need here. The aug I n plus 1 here is giving me the n plus first column, which is the b column. So this gives me a b entry, right? And you remember that formula that we found in general, that sequence of steps that we found in the last page, it was always a b entry, and then we started subtracting things from it. How many things we subtracted from it depended on how many things we calculated so far. And they were always entries of a matrix times previous x values. And that's what this is right here. It's building up the right value by continually updating the current x that we're on by those matrix values times the previous x values that we found, which is what is happening in this inner loop. So hopefully, this here then updates the x value, the current x value we're calculating according to that pattern on the last page. So it's pretty dense, right? It's pretty dense with i's and j's and so on, but I think that if you lay it out and you go line by line and you copy out the code and you try to see for yourself, you're gonna see how this works. And it's not actually as bad as it might look at a glance. But it's really important to have gone through that last page and understand where that formula comes from in the first place. And then at the end, once you've done all of those subtractions, look what you do. You divide by the current diagonal, aug m I. And that's that. And at the end of the day, display the solution. This will give us a vector of values at the end. So, a little bit involved, but at the end, I've got some white space, I've got some comments, and I can still do this in less than 30 lines. So it is actually pretty efficient, even though I'm not an expert by any means. Okay, a couple of little pointers to stop. Wow, we're at 45 minutes. That's nuts. Let's see. The simple algorithm assumes that we're working with non-zero diagonal entries, because otherwise we have to divide by a 0. So that's an issue. So this is actually really simple code, and if you wanted to make it better, you could make sure that you do some checks at the start to make sure they're not 0. If they are, then do some swaps, because we didn't talk about that as a valid step. So you could swap some rows to ensure we're good to go from the start. And a note on efficiency. The whole process to solve a system of n equations and n unknowns in this way. I think I referred to it way back when we talked about asymptotic order. But if you do the whole row reduction and then the back substitution steps, it takes, in general, on the order of n cubed flops for a computer to perform for n equations and n unknowns. So it's going to, in general, be the case where if you increase the dimension of a system by 1, right, so if you go from like as the dimension increases, the amount of steps required to go through the process goes up cubically. So it increases quite vastly as that system increases. And so it becomes a really big process, the bigger and bigger that a system gets. So that's, of course, the exact number of steps is going to depend on the actual entries in the matrix. If you have a bunch that are already 0, then maybe you don't need quite as many steps and you can skip some, right? The amount of zeros in a matrix is something that's kind of loosely called the sparseness of the matrix. Sparse matrices are ones where most of the entries are 0, and those are typically faster to process because of the fact that you can do operations really quickly that way. But n cubed in general kind of sucks. And one thing that we're going to kind of end the course with is a conversation about how we might be able to improve that situation. There are all sorts of algorithms to be able to solve systems of equations more efficiently. And we're going to touch on just one of them as an introduction to that before we call it a semester. And yeah, I look forward to that. That will be our last video, our next one. So why don't we bring it back? Hopefully you're able to follow along. I know that it's not the easiest thing to parse through some of those indexes and you know, some people are afraid of linear algebra to begin with, but you shouldn't be. It's really not that bad. It's just requiring a little bit of practice like usual. As you practice, feel free to contact me. Hopefully this makes some sense, and hopefully you recognize that really all we're doing here is an extension, a review really of linear algebra, but trying to codify it into a more precise algorithmic pattern. And if that code helps you to see that, if any of my words that are just spewing out of my mouth help you to see that, then awesome. That's all I need. Okay, so we got one more to go. Let's do it. I will see you then, and good luck with this stuff. Until next time, everybody.